Not really. All right, so we're going to start with electronegativity. And electronegativity, I think, when we're kind of bringing everything back about periodic properties, this is definitely one that we talk about. This is the definition of electronegativity. You can see I have the graph for it. Electronegativity is defined as when you have two elements that are bonding, they're already sharing electrons. Both elements, though, have the ability to pull the shared electrons toward themselves. And electronegativity is the measure of how much pull atoms have on the electron. The atom with the higher electronegativity is going to yank the electrons more toward itself. And then it's kind of gaining the electron from the other atom, which makes it partially negative. That's where we get polar bonds. I had mentioned yesterday, we're not concerned about the D block on the periodic table. The transition metals, they don't follow the same trends as other elements do. So the same thing is true here. Just look at the black dots, and you can see very distinct trends. Electronegativity starts low on the left on the row, and then it moves, as we move to the right, it goes higher. Clearly, it goes higher. And then we start the next row, starting low, and then it goes higher. Start the next row. Now this is where we get into D's. They start low and go up, and then to the next black one, up very obviously. So that's what goes on with electronegativity. It's a very clear, distinct pattern. There are a couple of noble gases that they have been able to make compounds with. I've never dealt with any of them. Like xenon has a couple of compounds that are made with it. Even krypton can make some compounds. They're not terribly common. Scientists have to beat up on xenon and krypton to get them to bond. But they would have values for electronegativity. That was why I worded this bottom statement the way that I did. It says, noble gases that don't bond, because you were probably told that noble gases just plain don't bond, don't count on the bond, but some of them do. So that was why it says that the way it does on the bottom. Okay, and then the next two slides are just going to go over what the trends are. Across a row, that's those connected dots, electronegativity is obviously increasing. You can see where the highest electronegativity atom is, the highest point on here. By far, the highest electronegativity element is fluorine. It's the best at gaining electrons. That's why fluorine has the highest reduction potential. We saw that in the last chapter. Fluorine is the most aggressive about gaining electrons more than anything else. So really an explanation of that trend is as atoms get smaller, the nucleus is able to draw the electrons more toward itself, and even shared electrons are pulled in by atoms that are smaller, more. Have they turned you away?
She said I needed a pass or something.
Oh my gosh, do you want to go back down?
No,
Sorry.
she gave me some soda. I don't know.
Okay. All right, you good with that one? The trend across the row. Atoms get smaller, electronegativity goes up. Now, as we go down a family, of course, atoms are getting bigger as we go down the family. The size of them is getting bigger. And so atoms are not as able to pull electrons toward themselves. I'll move this up some. Whoop, I'm going to lose my title, but that's fine. That was pretty low on the screen. As we go down a family, because atoms are getting bigger, they're getting bigger partially because the outer electrons can't feel the nucleus as much because of this thing we call the shielding effect. So electronegativity is lower. We can see this phenomenon when we look. The halogens are labeled on here, and you can see that fluorine is the highest geographically in the periodic table, and then chlorine is below it, bromine, iodine, kind of levels off like that, but it is starting high and going low. And we can see that in the other families too, like the alkali metals. That would be lithium, and then sodium, potassium, rubidium, cesium. Even our good old big boy francium is there. It's not as pronounced as what we have here, but it is going down gradually. That's electronegativity. Very simple. The trend is obvious, and no big surprises with electronegativity at all. Okay, now the last property of atoms that we need to know, this actually is not in Chapter 7, it's part of Chapter 8, but since we're talking about size of atoms, I thought this was the best time to put this in. What happens to atoms when they gain or lose electrons? The first thing I want you to see is the change is dramatic. There's a big difference in the size of ions versus the neutral atom. So what happens with ionic size is you have to think of it as how the protons in the nucleus are related to the number of electrons on the outside. When you have the same number of protons as electrons, it depends on how far to the right the element is as to how much the electrons are drawn in. But when an atom loses an electron, now it's got more protons in the nucleus than it has electrons around it. And that causes an atom, if it starts as this size, loses one electron, it just pulls the nucleus now with more protons than it has electrons to account for. It is able to pull the atom in. An atom gets much smaller, significantly smaller, when it loses an electron. And then when it gains an electron, it's the opposite that happens. Now you have more electrons than you have protons to hold them together. So there's not as much positive charge compared to the negative charge that seeks it. So the atom gets, it kind of balloons up and gets bigger. I have a graphic that shows relative sizes of, these are the alkali metals, starting with lithium through cesium. And these are the halogens, fluorine, chlorine, bromine, iodine. And we can see how what a big change there is in the size of them when they either lose or gain an electron. Sodium, for instance. By the way, the unit on here, I don't know if you can catch the unit. It's kind of a funny unit. It's an A with a little circle on the top of it. That's what it's measured in. And that's called an angstrom. Maybe in physics you've heard of angstroms if you have physics. It's 10 to the negative 10th meters. So if it says like the size of the lithium ion is 0.68, it's 0.68 times 10 to the negative 10 meters in diameter. In radius, I'm sorry, radius. So you can see the big difference in the size of these things. Just one electron is all it takes. And it's kind of cheating to use the alkali metals as an example, because the alkali metals have one electron on that outermost energy level. So when you get rid of that one electron, there's probably more of a change for these than the other elements, because it entirely loses an energy level when it loses that one electron. But you can see that there is a very observable change. And then the opposite when you have an atom that gains an electron. Look at bromine, for instance. It goes from 1.14, almost doubles its radius when it gains just one electron. It's got 35 protons in the nucleus, holding on to 35 electrons. But when it when it gains the one electron, now it's got 35 electrons. 35 protons in the nucleus. Those 35 protons are trying to hang on to 36 electrons, so it can't as well, and so the radius just gets bigger. Anybody have any questions about that? The next slide has a little exercise for us. I'm going to give you a pair of either atoms or ions or some combination, and I'm going to ask you which one is bigger, which one's got the bigger radius between these two. The first one should be really easy. Magnesium, the element, or the magnesium ion. Which one would be bigger? The magnesium element, yeah. The neutral magnesium is going to be bigger because with the positive 2 charge, that means it has lost 2 electrons. And not only is it now 12 protons hanging on to 10 electrons, which the protons are the bigger number, so it draws those electrons in more tightly. But also, when it loses 2 electrons, it has lost that third energy level of electrons. Now it only has 2 energy levels of electrons to hang on to, and it's not as far anyway to the outer electron. So definitely, magnesium, the element, is the bigger of these two. What about this one? Calcium, the element, the atom, versus the sodium ion. Who's going to be the bigger size on this one? Now I know that these are kind of offset. They're not in the same family. But you know what happens to sodium when it becomes an ion, right? It gets really pulled in more tightly. As opposed to calcium, which is still, it's 1 energy level bigger than sodium. So I would definitely identify calcium, neutral calcium, as the larger radius. Now between these two, the chloride ion or the bromide ion? Which one's bigger? Yeah, both of them have gained an electron and become bigger, but bromide being 1 energy level bigger than chlorine is going to be the winner on this one. Okay, how about, I like this one, the fluoride ion or the oxide ion? Which one do you think is bigger on this? All right, I want you to consider what's happening with each of these. Here's fluoride, so I'm going to do fluoride like this. Fluoride has 9 protons, atomic number is 9, and the 9 protons are holding 10 electrons. And then you have the oxide ion, where you have only 8 protons in the nucleus, and they're holding 10 electrons. Which one is going to not be